Airborne from Michigan State University, and I'd like to welcome you to today's Cause Teaching and Learning webinar. We're pleased to have as our presenter today Dr. Kevin Ross, who is an assistant professor in the statistics department at Cal Poly San Luis Obispo. For today's webinar, he will give a presentation entitled Symbulate, Simulation in the Language of Probability. The way the webinars work is that all listeners are muted during the webinar. You can ask questions at any time by typing them into the questions box. We'll be sure to ask those questions towards the end and give Kevin a chance to respond. You can also use the chat box if you're having any technical questions, and I'll try to answer those as we go. At this point, I'll turn things over to Dr. Ross. Kevin, go ahead.
Okay, thank you, Camille, and thank you for the introduction, and thanks to those of you out there who are listening in. This presentation is based on joint work with Dennis Sun at Cal Poly, and our research is supported by the Bill and Linda Frost Fund. So the motivation and what I'm going to be talking about today mostly involves probability classes, though some of the ideas would certainly translate to statistics classes, is that when I'm teaching probability, I want to promote this idea that students should simulate every problem. So literally every problem they come across, I'd like students to run some simulation to check their answers to get an idea of how the problem behaves. But writing programs from scratch involve a lot of issues that are tangential to the simulation, a lot of programming issues. And I've noticed that when I meet with students to discuss their simulations, it's hard for me to tell if they're having difficulty because they're having difficulty with the programming, or are they having difficulty with the probability concepts. And while I think programming is certainly important and an essential skill that students should have, in a probability class, my emphasis is on teaching those probabilistic concepts. So we got started thinking, is there a way that we could reduce the programming burden on students to get to those simulations faster so that students could really use the simulations to learn probabilistic concepts like random variables and distributions. And a key component of this is to simplify visualization, especially with respect to things like joint distributions or these concepts that tend to be a little bit more difficult or less concrete. So those were our goals, and we developed this package called Symbulate. It's a Python package which is available for free download from our GitHub site. And this is basically the abstract for the talk. We think it's a user-friendly framework for conducting simulations. It reflects the language of probability. I hope to give you a sense today of what I mean by that. And I think for students who are in a probability course, Symbulate syntax is fairly intuitive to learn. And the syntax of Symbulate reinforces the understanding of probabilistic concepts beyond just the fact that simulation itself is helpful in teaching and learning probability. So let me start with two initial examples to give you a sense of what Symbulate can do. The first is an example that students might see in a first course in probability or mathematical statistics. Here we have random variables x and y. They're independent. Each one has a Poisson distribution with different means, and we might want to simulate the conditional distribution of x given the event that the sum of the two variables is equal to 5. And so we want to simulate that distribution and compare with the theoretical binomial distribution. So at the top here is the Symbulate code for producing the simulation, and the bottom, the graph, is the output from that code. So we start by defining random variables x and y. We define them to be random variables, two random variables, so they have a joint distribution. Since they're independent, that joint distribution is the product of these two marginal distributions. So that defines the model in the random variables. Now we want to simulate values of x given this event x plus y equals 5. We want to simulate 10,000 values from this conditional distribution and plot them. So the second line here produces the plot down here with the spikes. Those are the simulated relative frequencies, and then we can compare to the true binomial mass function by plotting that, and that produces the blue dots here. So a couple things to notice. One, we actually define random variables first. The independence is represented by the product symbol. This joint distribution is the product of these two marginal distributions. Conditioning is represented with the vertical bar, just like it is when they're writing out math problems. When we call this sim 10,000 here, this actually simulates 10,000 values directly from the conditional distribution. And it's fairly easy to create a plot with the simulated and theoretical distribution on one plot. The second example is something that students might encounter in a more advanced class in probability that covers stochastic processes. We have a Poisson process. We have an exponential random variable, assuming the process and the random variable are independent. And we want to simulate the distribution of this random variable n at big T. So this is the Poisson process, but accessed at a random time, t. So here's what the Symbulate code looks like. And I hope you get a sense here that the way that a student would program in Symbulate is almost a exact translation of the way that the problem itself would be set up. So we define n to be a Poisson process. We define t to be a random variable with an exponential distribution. We assume that the random variable and the process are independent. And now we want to look at this random variable n at time big T. Well, the only difference is now we're using brackets instead of parentheses. But we can simulate values, 10,000 values of that random variable and plot them. And we get an idea of what that distribution looks like. So Symbulate reflects the language of probability. So when in a probability class, students learn concepts like random variables. Well, in Symbulate, you can define a random variable. And it's consistent with mathematics of probability. So when we talk about independence, the joint distribution is the product of marginal distributions. And that's the way that you specify it in Symbulate. And it requires minimal programming. In particular, this is a Python package, but Python's just the platform. Students need no previous experience with Python and very minimal previous experience with programming in general. It enables easy and effective visualization. There's one plot function that will basically produce a good plot for whatever that situation is, whether it's a discrete random variable or a continuous random variable or multiple random variables. And then a variety of probabilistic concepts are built in. I think Symbulate is very useful in undergraduate probability courses, but one of the strengths of it is that it can tackle a lot of problems in graduate courses too. And then it's compatible with Jupyter notebooks, which I'll mention what those are in a few minutes. So Symbulate reflects the mathematics of probability. The basic principle of Symbulate is that any probability model has certain components. And so any Symbulate simulation starts with these components. So it starts with a probability space consisting of the outcomes and whatever the probability measure is. And then on that probability space, you can define random variables or stochastic processes, possibly via transformations of other variables or processes. And then you have related events. And in particular, you might like to condition on certain events. Those are the components, the mathematical components of any probability model. They're also the Symbulate components of any probability model. When a student wants to run a simulation, these are the basic steps. You define the model itself, and then you simulate realizations from that model, possibly with conditioning. So it could be outcomes from the probability space directly, occurrences of events, values of random variables, sample paths of particular processes. And then we'd like to summarize the simulation results with plots or descriptive statistics to visualize distributions, approximate probabilities, or expected values. Okay, so I'm going to switch over now to this Jupyter notebook. And this notebook, so the Jupyter notebook is kind of analogous to the the notebook feature in R Markdown and R Studio. It's one document that contains both text and code cells. So it's arranged in these cells here, and the cells can either contain text or code. And if it's a cell that contains code, you can run these interactively. So I can run just this cell, and any output that that cell produces would show up right after it. So we import Symbulate using these lines, just these lines here that I'll load the package in. And so all I want to do now is give you some examples of what Symbulate can do, and to try to convey this sense that the Symbulate syntax is consistent with the language of probability that a student would learn in class, and that I think that makes it kind of intuitive for students to program here. So I'll start with a simple example first, a simple die rolling example. Imagine that we roll two fair four-sided dice. In this case, the probability space could be considered to be the 16 equally likely ordered pairs. And say we're interested in these two random variables. X is the sum of the two rolls, and Y is the larger of the two rolls. Well, first we start by defining the probability space. And in many elementary situations like this, the probability space can be specified by a box model. So this P defines a probability space P through this box model, We have a box with tickets labeled 1, 2, 3, 4, representing the sides of the die. We're going to select 2 tickets from that box to represent the 2 rolls of the dice. We're going to replace those tickets, and the order here matters. Now, this line of code just defines the probability space. There's no output to this line. Once this probability space is defined, we can now simulate values from it. So this is the result of one realization from this probability space, the outcome in which we roll a 1 and then a 4. And the second realization, we roll a 1 and a 1. And so we can simulate from this probability space as many times as we want. We can also define random variables. Now, mathematically, a random variable is a function that maps the probability space, the sample space, to the real numbers. That's the mathematical definition of a random variable. And the Symbulate definition mimics that mathematical definition. So we can define x to be a random variable. We specify the probability space on which that random variable is defined, p from before, and we specify the function that maps outcomes from this probability space to numbers. So x is the sum of those 2 dice, and y is the maximum of those 2 dice. Again, this particular line doesn't produce any output. This just defines the random variables. And that's one of the pedagogical advantages of Symbulate, is that the user can define these mathematical objects, like probability spaces, random variables, processes, separately from each other, but also separately from their simulated values. So this defines the random variables. Now, random variables are functions. So we can take a particular outcome, a particular pair of rolls, say we roll a 3 and then a 2, and then we can evaluate the random variables for that particular outcome. So x evaluated at this outcome gives us a sum of 5. Y evaluated for that outcome gives us a larger roll of 3. Now, we have these random variables defined, so we can also simulate values of them. So we have our random variable big Y. We can simulate 10,000 values of that random variable. We're going to store them as little y here, and then just display. And so this table just gives us a few of those simulated values of our random variable y. So this will be a list of 10,000 values. We can tabulate those simulated values by using this tabulate function here. So here are the possible values of the random variable big Y and the simulated frequencies, and we can plot those values. So if we just do y.plot, we get a plot that looks like this with the possible values and the simulated relative frequencies. We get this impulse plot because y here is a discrete random variable. There are many different summary statistics that are built in. If we wanted to estimate the probability that our random variable y was at most 3, we could count all the values of y that are less than or equal to 3, divide by 10,000. We could find the mean of the simulated values to approximate the expected value. And I tend to use this method, this extension method syntax here when I'm doing things. But you can also use other syntax where you just say mean of y, and that'll produce the same value. So that gives you a basic sense of what a probability space is and how random variables work. I think one of the main strengths of Symbulate is the ability to work with multiple random variables at once. And so we had these 2 random variables defined, x is the sum and y is the larger of the rolls. We might want to know what their joint distribution is. So we can simulate both x and y simultaneously for the same outcomes in the probability space. So this will simulate 10,000 values from this joint distribution and tabulate them. So now our outcomes are pairs of the random variables, and these are the simulated frequencies. We can display this joint distribution in a plot. Now, when you call plot in Symbulate, it will produce an appropriate plot for whatever data that you have. So, it's a discrete or continuous random variable. How many random variables are there? But then there are other plot types that you can call too. So in this example, displaying the joint distribution of the sum of the rolls and the larger of the rolls by this tile plot, where these rectangles represent possible pairs, and the simulated frequencies are represented by the color intensity here. And then we can also add the marginal distributions to that plot. So this is a nice visualization that gives students a sense of, well, what's the joint distribution of these random variables, pairs of values, and then also what are the marginal distributions. So in that example, we defined random variables by specifying the probability space itself. In many situations, we just define the distribution of the random variable. And you can do that in Symbulate too, and all the common distributions are built in. So we can define x to be a random variable with an exponential distribution, and then simulate it. And when we plot the simulated values here, this is a continuous random variable, so we get a histogram instead of the spike plot. One of the nice features of Jupyter Notebooks is that when you make multiple plot calls in the same cell, it will automatically output a single graphic with the plots superimposed. And so if we want to compare distributions, this is an easy way to do it. So here we're simulating values from a normal distribution with a mean of 1 and from a normal distribution from a mean of 2. And if we plot both of those things, then we can see how those two distributions compare on one plot without having to worry about adjusting axes or scales or anything like that. We can also work with joint and marginal densities. So we can simulate values from a bivariate normal distribution. When we simulate values here and call plot, it automatically produces a scatter plot. But now, what if we wanted to visualize what a joint density is more effectively, rather than just here are 10,000 values of the scatter plot? We can use the density method here, the density type of plot here, and it'll produce a kernel density estimate of this joint density, again with the color representing the density intensity. And so this gives some sense of what the joint probability density function looks like in this case. And as we saw before, we can add the marginal densities to the plot too. So just this one single call to plot with a couple different types allows us to produce a fairly sophisticated visual without a lot of programming required. Common stochastic processes are also built into Symbulate. So we can define a Poisson process N. Realization of a Poisson process, of a random process, stochastic process, is a sample path function of time. So when we call sim on a Poisson process, the output, the realization here, is a sample path viewed as a function of time. We can simulate lots of sample paths at once and plot them all on the same plot. So a plot like this gives students a sense of, well, at any particular time, I have a distribution of values. And so that allows students to kind of see what a stochastic process is all about. Like I said, at any particular point in time, we have a random variable. So n is my whole process, but I can say, what's the distribution of process values at, say, time 3.5? So I can call that random variable just like the mathematical notation. You know, we would use n parentheses t. Well, here I'm using n brackets t. So the Symbulate notation, Symbulate syntax is very compatible with mathematical notation. We can simulate 10,000 values of that random variable and plot them. And again, we can overlay the true theoretical distribution too to see how our simulation compares to what theory says. Okay, so when we get to independence, again, in terms of reflecting the mathematics of probability, when we're talking about independent probability spaces, we're talking about product spaces. So we can define two probability spaces and then make them independent by looking at the product of those two probability spaces. Same thing with independent random variables. If we have two random variables and we want to make them independent, well, we can say, well, let's define these two random variables by specifying their joint distribution. And we're going to specify their joint distribution as the product of their two marginal distributions. And this also illustrates when you have multiple random variables defined on the same probability space, then you can add them or otherwise transform them. So we can define random variables x and y, and then we can simulate values of their sum and get a plot that looks like this. Now, Symbulate reflects the mathematics of probability, both in what it can do and what it can't do. And that's what this next example is about. Imagine that we wanted to code this, what's the distribution of the sum of two independent normal variables? Well, a student might naturally try to write code that looks like this. Unfortunately, or maybe fortunately, I think, if the student tried to run this code, it would produce an error. And here's why. This first line defines the random variable x by specifying its marginal distribution. The second line defines y by specifying its marginal distribution. Well, to simulate the distribution of their sum, you need to know this joint distribution of x and y. And just specifying the marginal distribution of x by itself and the marginal distribution of y by itself, that information alone is not enough to say what the joint distribution of x and y is. And that joint distribution will affect the distribution of the sum here. So trying to run the code like this will produce an error. Now, if you want the random variables to be independent, you need to explicitly say that. Independence is an assumption of the model, just as much as the fact that this random variable has a normal distribution is an assumption that we specify. Symbulate makes you specify independence too. You can do that either like we did up here by using this product syntax. There's also this assume independent command where we can specify the two marginal distributions and then say treat these random variables as independent. And then this code will run without error. So, again, this reflects the mathematics of probability. When a student would write this code and comes up with an error, the student would say, why am I getting this error? And I can talk through this process of how, well, the marginal distributions alone are not enough to define the joint distribution. So events, we can define events. Events are subsets of the sample space. So this goes back to the example that I showed you first, where we had the sum of these Poisson random variables, and we were trying to condition on this event that z equals 5. Now, when a simulation runs, the event either happens or not. The outcome is either in that subset defining the event or not. So when we simulate values of an event, we either get trues or falses. So out of these 10,000 repetitions of the simulation, this event A, the event that the sum equals 5, occurred about 1,000 times. Once you define events, you can condition on them. And this is the example that I showed you at the beginning today. But again, with conditioning, we use the vertical bar. So that, directly reflects the way that conditional probability statements are written mathematically. And we can simulate values directly from the conditional distribution. So when I call .sim 10,000 here, it's going to run this simulation producing values. It's going to discard all the values for which the sum is not equal to 5, and it's going to keep running until it produces 10,000 values that satisfy that condition. So it simulates directly from the conditional distribution itself. And you can also use conditioning with joint distribution. So here's a situation where you have 3 random variables that have a multivariate normal distribution. This line here simulates the joint distribution of y and z. Those are the blue dots in this plot. And then we can simulate the joint distribution of y and z condition on x being equal to 1, essentially. Those are the green dots here. And so students can see how conditioning can change the joint distribution of 2 random variables. Transformations of random variables are also random variables, so you can apply functions to random variables and call them like that. Now, I notice in this example, you define u to be the random variable, and then you can define x to be another random variable by transforming u. So you're not just transforming the simulated values, you're transforming the variable itself, and then you can simulate from x directly. You don't have to simulate u first. Symbulate also has a distribution calculator built in. I'm going to skip that for now. One useful feature of Jupyter Notebooks that I want to make sure I get to is these widgets. And widgets are a way to make a lot of these simulations interactive. So say I wanted to produce some central limit theorem type demo. This is one way of simulating the sampling distribution of the sample mean, say for samples of size 5 from an exponential population. Say I wanted to see what happens to this plot when n changes. Well, you can take the Symbulate code here and add a couple lines of Python code to add this widget, that's called. And what this does is basically takes this plot here and produces a slider for the value of n. And then you can change this slider and interactively see how the distribution changes as n increases. So I say these widgets give a way to appletize Symbulate code. You can write Symbulate code for a particular problem and then add these widgets to see how the problem changes when you change various different parameters. Now, a lot of the examples that I have here don't have any programming involved. It's all Symbulate code. You could certainly incorporate programming too. And so this is one example of how you might incorporate actual programming into the simulations too. But in many situations, the simulations can run without any coding at all. Okay, so I'm going to stop there for the examples and just say a couple more words before questions. So going back to my slides, now there are more Symbulate commands that are on this slide, but vast majority of situations can be handled with the commands on this slide. And all I want you to see is that this is a relatively short list of commands. So students can pick up this syntax, I think, pretty quickly. There's not a lot of different commands here that the students need to know. So it minimizes the programming burden on students. Now, a lot of this you could do in R, and R is great, and I don't think that R is bad, but I do think there are some pedagogical advantages that Symbulate has over R when we look at the syntax. So comparing side by side, this goes back to the first example I showed, where we had these independent Poisson distributions, and we wanted to look at the conditional distribution. Well, in Symbulate, you can actually define random variables. In R, you simulate values from a distribution, but you don't define the random variables themselves. And these are tricky concepts for students. The difference between a distribution and a random variable and simulated values. These are hard concepts for students to learn. Well, Symbulate kind of reinforces that distinction because these are separate objects in Symbulate. The random variable is different from the distribution, and that's different from its simulated values. In R, you have different functions, right? You have RPOIS, you have DPOIS, you have PPOIS. You have different functions for the same Poisson distribution. And the parameters of those functions involve both parameters of the distribution itself, but then also parameters of the coding function. Well, in Symbulate, you just have the distribution. The only parameter of this Poisson is just the mean of the Poisson distribution. In Symbulate, like I said, you have to explicitly assume independence. It's part of the model, just as the fact that these are Poisson random variables are part of the model. You have to reflect that here. In R, that's implicit in the fact that these things are generated independently. In Symbulate, you can actually add the random variables. So here we define this new random variable z to be the sum of these other two. In R, you're adding vectors of simulated values, which isn't quite the same thing. In Symbulate, conditioning is represented by the vertical bar, and you can simulate directly from the conditional distribution. In R, conditioning, you do it different ways, but it could involve logical subsetting, which isn't always the most straightforward thing for students to understand. Plotting here, this is a discrete random variable, so it'll plot it directly. In R, it requires a little bit of manipulation before you plot it. And then also, you can simulate 10,000 values directly from the conditional distribution. And this problem setup would only simulate about 1,000 values that would satisfy this condition. It would take more work to get 10,000 values for which this condition is true. So I think R is great, and there's a lot of advantages to R, but I do think that Symbulate has some pedagogical advantages over R, in particular in terms of reinforcing these probabilistic concepts. I'm going to skip these next few slides. A bunch of these ideas came up whilst I was discussing the examples, but just evidence of how Symbulate reflects the language of probability. We define probability space, these events, random variables. These are all separate objects defined separately in Symbulate and defined separately from their simulated values. And so I call it a simulation with minimal programming. There's this .sim command that will run and produce the appropriate realizations as long as you've set up your model. So the work is in defining the random variables in the probability space and the processes. And if you define that model, that probabilistic model correctly, when you run .sim, it'll produce the right thing without needing to write loops or initialize or update variables or vectorize code or install any additional packages or libraries. And I think one of the big strengths of Symbulate is the graphics. And this is something that we're working on actively now. I do think there's a lot of nice features already, but we're trying to improve them even more. But there's this universal plot function, which will produce the right type of plot. So, whether it's based on whether it's a discrete random variable or continuous, and the ability to overlay several plots on the same graphic and compare distributions and things like that without needing to know R or packages like ggplot. And I think this is especially important in pure probability classes in which, there might be students there with no statistics background at all, and they have very little background with descriptive statistics, let alone, programming or R or things like that. So I think I'll stop there. I'll just say that Symbulate is available for free download at our GitHub site, and this GitHub site also includes documentation files with examples and also some getting started tutorials. So thank you for listening, and I'm happy to answer whatever questions you have.
Thank you, Kevin, for this production. I am blown away by how beautiful and simple you've made all of this. That's really impressive.
Glad to hear that.
I'm thinking back to my probability days and wishing I'd had something like this when I was trying to learn it. So one question those of you who are listening, if you've got questions and want to type them into the question box, I can pass those along to Kevin as we go. One question from Anna says, how have you thought about incorporating animation into Symbulate?
We've certainly thought about it. We haven't gotten that far yet. The main way that we've incorporated so far is through the use of these widgets where you have to actually scroll the slider and things like that. There are ways that you can incorporate animation. It's on our list of things to do, but it's kind of a little bit further down the line. And I should say that I don't think I said this at the beginning, but I mean, this is a Python package because my co-author, Dennis Sun, is very familiar with Python. I had no background in Python before starting this. And so I'm still learning what Python can do myself. But I just want to reiterate that, while the Python is the platform for this, you really don't need to know Python at all to do most of what Symbulate can do. But yeah, we would love to put in some animation in the future.
So that kind of leads into my question that I had for you, and that is, so do you have most of your students at Cal Poly working in Python? If they come into a probability class without a statistics background, do you say, okay, load Python onto your computer and here's how we're going to do this? Just kind of what's the culture about that at your university?
Yeah, so I've used this program for 3 quarters now. So it started about fall of 2016. That's the first time we used it. And I haven't taught stat majors actually with this yet. It's mostly been a probability course that's just primarily taken by engineers. Those engineers have had a programming course. Cal Poly switched over to teaching that introductory programming course more in Python. So now students are a little bit more familiar with Python. But when I first taught this, a lot of those students had never seen Python before. So they've had some exposure to it. But even among those engineers, their programming experience can be widely varying.
Right.
So we use Symbulate. We do build a little bit of Python in. That last example that I showed you there, we have built some Python coding in. But yeah, I kind of teach this from the perspective that students have never seen Python before and have actually had very little programming experience before.
So we have another question from John. He says, would you suggest Symbulate or R for a class where students are stats majors, say a math stat class?
So yeah, that's definitely
transferring of those R skills.
Yeah, that's definitely a good question. I mean, Symbulate has a very particular purpose, and learning R, a student is not going to go on a job interview and say, I know Symbulate. Like, nobody's going to care. Nobody's going to know about that, right? R is a skill. But I definitely think you could use both in conjunction, and that's what I plan to do. I'm teaching our second course in probability in the spring, and I plan to use both Symbulate and R. I mean, I certainly want students to know how to program from scratch. I want stat majors to know how to program a simulation from scratch, and R is a great place to do that, and it's good to learn R skills. But I don't want them to have to do that for every problem. And I would like them to get in the habit of simulating every problem. My colleague Alan Rossman likes to talk about the SIM paradigm, so simulation, intuition, mathematics, and approaching every problem from that perspective. And I think Symbulate makes that idea much, much easier. So like literally every problem translates from the page to simulate code in just a few lines. So I do think, especially for statistics majors, combination of both Symbulate and R. Symbulate for the day-to-day stuff, kind of simulate every problem, and then R for situations where you really want to code simulation from scratch.
Okay. Robert Delmas is asking, students can use the same symbols to represent random variables and output from a process. Do the students show any tendencies to conflate random variables and the output for example, lose track of the X, the random variable, and Z, a collection of outputs from running a process?
Yeah, that's a good question. I mean, there's certainly nothing preventing a student from saying, you know, big X is the random variable, and then I'm going to store the simulated values as big X. You know, I don't have a lot of data on that other than what I've seen students in class. I mean, the way that I try to attack that problem is just, you know, by example, right? So whenever I run a simulation, I always say big X is the random variable itself. And then if I want to store the values of that, I store it as little x. Just like I would in class, you know, when we write things on the board, we write the probability that big X equals little x. And I hope that students, you know, learn that notation, you know, writing it down by hand, what it means when they say probability that big X equals little x. With enough repetition, they'll get that idea. And I'm hoping with enough repetition, they'll get the Symbulate idea too. But you're right. I mean, there's certainly nothing preventing a student from saying, let's store the simulation results as big X.
And if people are having trouble like downloading it or getting started with that, are you amenable to being contacted directly through your email or through GitHub?
Oh, sure.
How do you prefer that?
Yeah, you can certainly email me. That's fine. So when we first used this, we had students actually download Python through the installation called Anaconda, and then download Symbulate. And I didn't find that students had any more trouble downloading and installing this package than they generally do when I have them install R or Jump or anything like that. I mean, there's some, you know, unfamiliarity here if you've never seen Python before, but the actual installation of it I didn't seem to encounter that many more problems than I did. I will say that this past quarter when we used it, we ran everything through Jupyter Hub, which is similar to RStudio Server, where we just put everything on a server and students could just log into the server and run Symbulate through that. And that actually worked really nicely.
I bet. All right, well, thank you so much for presenting this for us today. And thanks to all of you for attending. We do have a full slate of additional webinars scheduled in the coming months. So I encourage you to keep an eye on your email or on the causeweb.org website for announcements. Thanks again for being here and have a great day, everyone.
Thanks, everyone.